Everyone, for this mini lecture before the group operations adventure sheet, I'm going to split it into two parts. One will be a review from some of the terminology that we learned last week, and one will be a sort of primer on group homomorphisms. So in this mini lecture, I'm going to review some of the terms from last week. The first being group. So I'm going to let G be a group, and we saw last time that this means that G is a set with an operation. So maybe I'll specify the operation just to make my life a little bit easier later on. And I know that the conditions required to be a group are that G has to have an identity, every element of G has to have an inverse, and my operation must be associative. Okay. We also learned the term subgroup, where we say that H, which is a subset of G, is a subgroup if it is also a group itself. Okay, but let's look at what this means, because the definition here is a little bit different, or what we need to check here is a little bit different than what we need to check to verify that a set with an operation is a group. It will still be the case that we need to check that a subgroup contains the identity, and because the identity for G is unique, it needs to contain the same identity. We'll also need to check that for every H in H, its inverse as an element of G is also in H. And then to check that something's a group, I need to check that my operation is associative. However, it will come to me for free that if my operation is associative on G, that it's associative on any subset of G. So I don't need to check associativity for subgroups. But in exchange, what I do need to check is that my operation is actually an operation. That is, I need to check that my subgroup is closed under the operation. So I need to check that A and B in H implies that A star B is also in H. So these are the three things that I need to check to verify that a subset of G is a subgroup. The difference being I have to verify closure instead of associativity for the group. Okay. I'd like to highlight some other terms that we discussed last time. We discussed the order of a group, and sometimes we denote this by putting straight lines on either side of G. The order of a group is the number of elements in the group. But we also discussed the order of an element. Where the order of an element is the smallest n, the smallest integer n, so that when you apply the binary operation of n G's, you get the identity for the group. So this means n G's here. And so one of the questions that we should discuss in the Canvas discussion is why we use the word order for these two seemingly different objects. And your Group 2 adventure sheet gives some introduction to this, but hopefully we'll discuss it more in the Canvas discussions. That we're using the same word for two seemingly different meanings. Okay. There's a couple other definitions from the Groups 2 adventure sheet that I'd like to highlight because they'll be used throughout this class and it will give us nice language to share. And those are product groups, similarly to product rings, so if I have two groups, say G, and I'll say the binary operation on G is star like this, and H, and I'll say the binary operation on H is a smiley face. I can take a product group, G times H, where the elements of G times H are some G and G, and H and H. So the elements in G times H look like ordered pairs of G and H. Okay, and then we ask, how do we multiply? What's the operation on GH? And the operation is just using the operation on each term separately. So what this means is if I have G1 and G2 in my group G, and H1 and H2 in my group H, if I wanted to apply the binary operation of G times H to G1, H1, G2, H2, by the way, here I'm applying the binary operation, but I haven't given it a name, so I'm just going to leave it out. If I want to apply the binary operation of G times H, this will be G1 star G2 and H1 smiley face H2. From doing this, maybe you are starting to see why we sometimes leave out the operations, because it would be much simpler to just write G1, G2, H1, H2, and leave the reader or mathematician to decipher that this means the binary operation of G and this means the binary operation of H. But in this introduction, I'm going to do it both ways, just so we have some experience with translating between those two different languages. Okay, so this is the notion of a product group. Just wanted to summarize this in words, verbally. I'd also like to review the definition of generators from last time, because that gives us nice language. Generators of a group. The best analog that you've experienced so far is a basis for a group. Actually, a better analog is a spanning set for a group. Or a spanning set from linear algebra, where a spanning set was a set of vectors that you could take linear combinations of to obtain any vector in your vector space. Likewise, the generators of a group are a set, so if G is my group, the generators of a group are a subset, possibly infinite, but let's, for our own sake, assume that it's finite. It's a set of elements in the group such that every, and I'm going to say H just so I don't keep writing G's, even though these are different G's, such that every H in G can be written as a product, meaning under the binary operation of G, G1 through Gn. And if our group is not abelian, we could end up with something like G1, G2, G1. So they don't have to be written in order. But if our group is abelian, we can ensure that everything is written of the form G1 to the P1, G2 to the P2, so this is non-abelian. This will not be equal to G1 squared G2, or won't necessarily be, but if we are abelian, we can ensure that everything is of the form just combine all the G1s together, combine all the G2s together, combine all the GNs together. Okay, so I just wanted to introduce this language to ensure that you've seen it, to ensure that you have some familiarity with it, because it will be nice to be able to refer to the generators of a group in the future. Thanks.